So when I start to talk about the process, that means the procedures. Again, I want to start from the example of the track positioning. Basically, the filter is an iterative algorithm. You do it again and again and again with one cycle after another cycle. In each cycle, there's two phases, the prediction phase and the update phase. That's the big picture. So the prediction phase is what we talked about, the phase of data ranking. The track uses its own old position and record its own acceleration and the steering direction based on the physical science law, Newton's law. You can estimate the next position. That's the prediction phase. But because this is a stochastic model, after you do any estimate, we always need to give a prediction of the covariance. That means how much total error you could estimate to have. So the prediction phase have two calculations. One is the data ranking component, just the prediction, your next position. Another one is estimate your covariance. The next stage, in the update phase, we're going to use the outside reference and the measurement to help track the track position. Now, in this case, we use GPS. Well, GPS uses the satellites as references. So we use the measurement to compute the amount of uncertainty, because if you are on the boat is under some current. If the boat drifts hundreds of miles away, you never feel by your internal devices. So in that case, the measurement make a huge difference to correct your prediction. That's the key word, to correct. So the key concept is the covariance really is relative to the prediction from the previous phase. What determine your new measurement, how much will affect your updated measurement. What does that mean? Let me put it this way. You, the truck driver, predict yourself if in this position. That's your prediction. From the predicted position, you can figure out the GPS signal, the distance to a reference. Let's say the distance is going to be something like that, whatever matrix. But the measurement will give you another kind of measurement from outside view. And that is the difference. The more this difference is, and the more you're going to correct yourself from the previous prediction. We'll look at the more detail, but the key word is compare the measurement based on the GPS and compare the same quantity based on your prediction, like that. So what is the signature without math? Okay, that means a qualitative model. The data ranking have a shortcoming. It tends to be drift away and accumulating the error. The measurement of GPS can pull it back into the real position. That's when the GPS is in good shape, have all the signal right, weather is good, no multipathing, something like that. The data ranking has an advantage, it's more smooth and steady. That means if I'm here, the next half second, I won't jump into this, like a GPS might give it to you. At the worst, I'm going to go to like that one, a little change. That's what I mean, smooth and steady. So if you add this little data ranking, which is accurate in small scope, like a few steps, that will correct the GPS big mistakes, will not disturb the system to the point become dramatic change and the noise. Now, GPS can give you error hundreds of miles away, you believe, when the weather is weird, signal is weird. So now let's look at the calculation elements, such as what is the initial condition and what we call it input, and look at the output, and look at the steps, what a calculation we really have to do. So as an input, I need to have an initial guess. For example, just how GPS itself works, you can wildly assume your initial position is right at the center of the Earth. Of course, nobody lives in the center of the Earth. We all live in the surface of the Earth. That's fine. And you need to also give a little bit of the initial velocity. You can give just 0, 0. That's all fine. Another thing is the deviation. The covariance matrix are based on the deviation of those estimates from one to another. But you can start with an empirical data. How much should be reasonable? Give those covariance matrices. Because the initial condition have not much to the final say, you can give a little bit just reasonable information. For the next step, we call the control variable you need to know. I'm still talking about the input, what you need to put in your calculation if you write your own program. Well, the truck needs to know its acceleration, how much the accelerator panel is pushed down, and the orientation of the steering wheel. In like if I do it every 10 milliseconds, the steering wheel should have just one direction. That's good. And other than this, of course, each cycle of the calculation, you need to get one GPS measurement from 4 to 5 at least satellites. Or say just to get the GPS estimation. That's fine. Now go to the prediction stage. The prediction stage, now here you cannot see the direction because I give you just the one dimensional. But you can use the position and the velocity to do the data ranking. Then the new position, simple idea, that n means new, equal the old position at your speed times the change of time. So how long from the current observation to the previous observation, that's the dt. That's a 2D data ranking. Other than this, you need to look at the covariance matrix. I'm going to give you the simplest way. Usually, you get a sigma, that's a standard deviation, multiply the identical matrix, usually sigma square, that's it. So if it's in 2D, that's all you need. So this we call it the white noise. If you have not learned the statistics before, go to read the class notes. I have a brief review about that. So now it goes again back to the update step. In that step, now we introduce a few more concepts. One is called the innovation residue. And that residue was an error measure the difference between the position given by the GPS and also the prediction position above. And all you need is to measure the difference of your prediction and the position given by the GPS. And then there's another innovation covariance. That covariance will connect the predicted state and the measurement of the covariance matrix. We're going to look at the detail later on. Based on those differences, basically the measurement tell you how good your prediction is if I assume the measurement is right. But sometimes the measurement itself is not right, then we need to do a blended estimation. Then we introduce the key concept. It's called gamma gain. Typically, the literature uses this little k, small k. The little k stands for Kalman, his name. Small k means the k step of the calculation. Well, based on the residues above, we give you the best, we'll call it optimized weight. And we use that constant to update your estimated position. In other words, I give a little bit of credit for your prediction. I also give some weight for the measurement, and then combine the two measurements. Then I get this new position estimate. And then finally, I need to update the covariance matrix. Okay, I hope you're not too bored so far, and still the easy part.